The last section of Chapter 5 deals with probability that is conditional on something else happening beforehand. Here are the objectives that are dealt with in this section. The key issue is that the probabilities that we're going to deal with and the tools we're going to use are going to have to do with probabilities where the second probability depends on the other one happening first. So conditional probability, a probability of a second thing happening might change if the first event has occurred. And so this whole thing is about conditional probability. And we can look at the probability of something. If we want to know that the probability of like an event B happening, given that A has already happened, we write it as the probability of B given A. And sometimes B and event A are independent of one another, and then it's really easy to deal with, and sometimes we have to pay more attention. That's what this is all about. So the formulas that are used for conditional probability are ones that you certainly can use and you certainly can memorize, but they're not intuitive. So if you want to look at other ways of calculating, that's more than lovely. But the probability of A given B, you're just going to look at the probability of A and B divided by the probability of B. And that's what that means, and vice versa for the probability of B given A. But we'll look at other ways of thinking about it. So conditional probabilities, one of the visuals we can use to understand conditional probabilities is a two-way table. Two-way tables allow you to look at marginal probabilities, which are just straight up probabilities. What's the probability of something happening? Like in this case, they've defined event L as being below B. So the probability of someone having a grade below a B, regardless of the school that they were in, is 3656 out of 10,000, or about 37%. These, on the other hand, are going to be conditional probabilities. So you're looking in this one right here. You're looking at the probability that it's an engineering school given that they got below a B. So since you're talking about given that they got below a B, you're going to go ahead and focus on this column this column right here, because the given is below a B. So you go ahead and take that 800 that's in the engineering and physical sciences part, given below a B, so that that's where your denominator comes from. Same thing with the converse. I've already got it in red here. Since this was given that you're an engineering or physical science school, then that's where your denominator is going to come from. And then you're looking in the column for 800 out of the 1600. So that's conditional probability. And when we're looking at the probability that both events occur, you can use the general probability rule, which is the probability of A times the probability of B given A. This rule says that for both to occur, first one must occur, then given that the first event has occurred, the second must occur. So we're looking at the probability that both occur, which is why we're talking about that intersection, and we're talking about the word and. Both occur. So here we have a tree diagram that looks at the idea that 93% of teenagers that were asked use the internet. So here we see the 93% on this part of the tree diagram, and that's the kids that do. And then down here, because this is a valid probability model, we're going to have a total of 100%. Either they did, 93%, or they didn't, 7%. And then 55% of those kids that have used the internet, which is over here, 55 had posted a picture on their profile, and then the other 45 had not. And then down here, because these people had never, of course, they have not posted on a profile because they don't use the internet, and it's a 100% chance that they don't. So in each branch of a tree diagram, has to equal 100%. And then since we're looking at the probability of both things happening, we're going to go ahead and look right here on this part of the tree diagram. And the probability that they're online is 93%. And the probability that they have a profile given that they're online is 0.55. And then you're going to go ahead and multiply them. So this is the probability that teens are online and have posted a profile. So that's how you use a tree diagram to help you there. Another example of conditional probability where the two things are not independent are when you're pulling cards from a traditional deck of cards. And traditional deck of cards has 13 of each suit, 13 hearts, for example. So if we were trying to find the probability of getting 2 hearts in a row when we have a full deck of cards, there would be 13 out of 52 chance to get the first heart, right? And then the probability of getting a heart, given that we already got a heart, that means we're going to have only 12 hearts left and only 51 cards left. So then we would go ahead and multiply 13 times 12 and 52 times 51 and do the division, and that would give us our probability. So this is a heart given a heart, and it does change the probability. So independent events means that the outcome of one event does not affect the other. And if that's the case, all you have to do is just multiply the probability of A and the probability of B because they're completely independent of one another. We're going to be looking at situations that are independent, and we're going to be looking at situations where you take the probability of A and then the probability of B given A is going to be a little different. So we're going to talk about that, and it depends. So here we have this notation. When events A and B are independent, we can simplify the general multiplication rule. Because A and B are independent, the probability of B, given that A has already happened, is just the probability of B because they're completely separate from one another. So if A and B are independent events, when you're finding the probability of A and B, remember that's your little intersection, it's just the probability of A times the probability of B. So here we have the sample space of the idea that we're going to be flipping 2 coins, and what's the chance of flipping 2 heads on a fair coin. So we can look at the sample space here, which is just a simple list, and also we can find that from that simple list that we have, we're moving here. We have 1 way out of 4 ways to get 2 heads. So that's one way that we can calculate this. The other way is to look at the idea that we are talking about 2 independent events. And since this is also a tree diagram for the same sample space, but we don't have to even draw the sample space since we're talking about 2 independent events. The probability of getting 1 head is 1/2, and the probability of getting another head is 1/2, and since they're independent events, you just multiply 1/2 times 1/2 is 1/4. So either making your sample space or multiplying, that'll give you your probability. Another example of this is the Space Shuttle Challenger disaster, which was when I was a freshman in college. It was very upsetting. It was determined that one of the parts of the shuttle's booster rockets was to blame, and the O-ring joints had a probability of functioning properly at really close to 100, but not quite. And since there were 6 in the shuttle, they could calculate the probability of it working, and so you would calculate the probability, because they're independent of one another, 0.977 6 times, and so there's an 87% chance that the shuttle would work well, it just launch safely, but that does leave you with a 13% chance that doesn't, which is a bummer. Anyway, independent events, you can just multiply them to find the probability of them both happening or them all happening. when we are looking to see if two events are independent, sometimes it's obvious, like flipping two coins and stuff like that. But if we're looking at a two-way table and we're trying to decide if there is an association between two events, and we find out that they are independent, there's a way to look at that, and we're going to look at that right now. If the two events are independent, the probability of A given B is exactly the same as the probability of A as if B didn't happen at all, or the probability of B given A is exactly the same as probability of B, then we can consider the events independent. We're going to look at an example. Okay, so we're going to go ahead and look at if two events are considered independent, if the probability of A given B is the exact same thing as the probability of A, because that just means that they're not related to one another at all. So we're going to look at probability of event A, which is being female, and that's a marginal probability. Super easy. We can go ahead and just take the 180 females out of the 240 total, and that's 75%. And then the probability of being a female given that they own a sports utility vehicle, that is in this column right there, and that's 135 total females that own sports utility vehicles, and that ends up being about 87%. So because these probabilities are not the same thing, then they are dependent on one another. That doesn't imply causality or anything, but they're dependent on one another. So that's how we check to see if it's independent. If the probability of one given the other is not equal to just the one thing, then hi everybody, bye.